let's continue with some people who also ask questions with regard to whether light curves or not, whether light, and the question again there is whether it swerves or deflects or curves. Are we talking about a ray curve, a curved ray, a bent banana? Is that what we're talking about? Or are we talking about a little ball that is, curving or following a curvilinear path through space? Those are not the same, not equivalent. And that's more or less the problem here. A fellow says the following. He says, how does light turn a corner? And that's the wrong question. That's the wrong question, okay? Because he's using the word light. He can't use the word light. He can't use the word ray. He's got to tell us what he's talking about. Is he talking about particles, or is he talking about waves, or some other proposal that he's got, okay? And so if you have a stream of particles, you cannot turn a corner, okay? So if he's going to simulate it with a stream of particles, he would have to tell us how he envisions those particles turning a corner. And a wave is the same thing. How does a wave turn a corner? That's all he's got to say, okay? And here's a picture that I've got, okay? Let me get this one out, of light coming between the door and the wall, okay? And you have light coming through there. And apparently light is curving around. You can see light, at least from the left side, is turning left as soon as it leaves the door or comes through the door. And the light from the right is curving as it comes through the wall, okay? But obviously we can do this with straight lines. There I've put the straight lines for you, okay? You can see the red lines there that I put. And you can see that this can be done all with straight lines. In fact, light always travels straight, rectilinearly, in other words, right? If we're going to talk about travel, there's really no real travel under the rope model. It's just torsion, in situ torsion. So there's no traveling. But if we're going to talk about travel, yeah, we can say that light travels straight. The signal travels along the rope. So if the rope is taut, it had better be straight. In other words, it should be traveling rectilinearly, propagating rectilinearly along the rope, because the rope is taut and it's the torsion of the rope. So it's very straightforward, right? And yeah, here you have it with a rope. Here you can see the atoms there. I put some green atoms and just a few of them. And you can see that if the red lines are the ropes, right? And I didn't put all the atoms, all the ropes, obviously. But you can see that from atom to atom, you have a straight line, and that's a rope that's connecting any two atoms. So yeah, we can do it with particles and with the rope, no problem. The particles are the atoms. So any atom there that you can see in that room, right, will be connected to all other atoms by straight ropes, taut ropes. That's really the correct word. They're taut. They're stretched as tight as possible. And here you can see the model, okay? We have the atom pumping back and forth. They torque the rope, and by torquing the rope, you can see that the torsion really doesn't travel anywhere. What it is, it just gives a thump at the both ends at the same time. So you could say it travels in both directions, opposite directions simultaneously, okay? Because both atoms receive a bump right at the surface of the atom. So that's our atom, and so yeah, we can explain straightness. We can explain why light always travels straight. Okay? And here is another piece of evidence that you can ponder, and this is evidence. There is an explanation here. The explanation is the following. Here you see the Earth, and what we have is a laser that is a big monster laser that's pointed from the Earth to the retroreflectors on the moon. And you can see why light always travels straight, because whether the moon or the Earth move is irrelevant. All the atoms of the moon are tightly bound to every atom on Earth, so the ropes are all pulled as tight as they can be, and the torsion travels along a straight rope. So the moon can go anywhere it wants now, because the light is just going to travel along the rope, And at the same time, there you see the cause of gravity. As the moon approaches the Earth, you will see that the ropes fan out. Okay, so we have both. We have like a grand unified theory here. We have both light and gravity in a single mechanism. But the point here is that the ropes are stretched as tight as possible, and the torsions travel along straight ropes. Okay, and that's why you receive the light in your eye, because every atom in the room is connected to your eye through the electromagnetic ropes. That's how simple it is. Okay? Okay, why can't we do it with particles? Well, here's the simulation for particles. This is why you cannot do it with particles, okay? You have this is the sun, okay? And the sun is made out of atoms. Every atom in the sun, well, first of all, the sun is twirling, right? It's spinning, right? But then every atom in the sun is also spinning and moving around and doing whatever. And so any photon, any particle, any discrete entity that you want to mention that comes out of every atom that makes up the sun has no chance. A whole series of them coming out of one atom has no chance of traveling in a straight line. It looks more like a sprinkler system. It just goes around and around and around, sprinkling all these particles in curves, never in a straight line. And that's where the particle hypothesis dies completely. Okay, and then we have here the wave version, the transverse wave. This is what a transverse wave looks like. Okay, this is the one proposed by quantum mechanics. It's the one that's been analyzed for at least 2 centuries now. Okay, they had this transverse waves. Okay, and so what are we staring at? Well, we can't use this as a mediator for light because it's made out of vectors. They call it field, so we have fields and vectors, both of which are mathematical concepts. You cannot say that a mathematical concept is a mediator of light. And so the wave, the transverse wave, dies right there and then. In fact, here you see a comparison of what happened. They confused the rope with a wave, with a transverse wave. So they were always talking about these transverse waves when what they were really looking at is the torsion, in situ torsion, of a rope. And you can see why they got confused, because they are structurally very similar, okay? The only difference is that the wave cannot explain c equals frequency times wavelength. C, the velocity of light, is a constant, and it's 300,000 kilometers per second. And when you raise the frequency, you have to lower the lambda, the wavelength, and vice versa. And with a rope, you can explain it very easily. If you increase the number of links for the same amount of rope, you can do this at home, you will see that the links will become shorter, and vice versa. When the links are longer, well, you have fewer links. Very simple. That's the equation of a rope. What you see in there, c equals frequency times wavelength. So you can see why they got confused, and they thought of a rope as a transverse wave, and to this day. Okay, and what is a wave made of? Well, sometimes they say it's made out of particles, because what is a wave made of if not vectors and fields? Well, here's a wave made out of particles. And no problem, we can accept that. The only problem is what makes each particle go up or down. I mean, are they tied together? Are they bound one particle to the other? So again, we have a problem here, because all these people just make assumptions, but they never illustrate what they're talking about. And because they cannot illustrate or don't illustrate, it's that they can never explain, because we don't have the images that we need to understand the presentation. Okay, here we have another fellow, and he says he does Mereology. Okay, Mereology is a religion invented by first the mathematicians. They passed it on to the philosophers on the other side of campus, and they created a cottage industry of Mereology. What is it? Parts of whole and temporal parts. They divide things up, and they say what something is made of. And this fellow has this in the back of his mind, I guess, and he says, I can describe a singular part of a medium as having shape, location. Yet you deny the existence of a medium composed of many such objects. Okay? I don't deny that the issue is something else, so I don't know where he got that. I would say that a medium is a composite object. That's where we have a problem. No, a medium is not a composite object. That's an irrational definition, okay? And that's an irrational notion. as in an object composed of many smaller objects. That's irrational. How is that not rational description? I'll tell you in a second. There are many examples of composite objects. Yeah, I'm sure there are. If your rational model has no way to recognize composite objects or composite motions or composite processes, then it can't possibly be describing nature. Okay, so what's the issue? Well, the issue is we have to take this poor fellow to kindergarten physics. See, all these people, they want to do college physics, high-level physics. They have never gone through kindergarten physics. They've never gone to first grade. And so let's start at kindergarten physics. I hope some of you who've been around, I hope you don't get bored too much, okay? But I got to go through this stuff because you have people like him that don't understand basic stuff, kindergarten stuff, something that a 10-year-old would be able to tell them. So let's start there, okay? And here it is. Welcome to kindergarten physics, okay? Today, children will learn necessary word salad to do physics. In physics, all objects are made of a single piece. Let's repeat that because I don't think he understood that. All objects are made of a single piece. They're all continuous, made of a single piece. Okay, an object is that which has shape, and there you see some synonyms, including the word he was raising question of, medium. A medium is the same thing as an object, a thing, and it's all made of a single piece. Okay, and so he might say, well, that's your opinion, Bill. Okay, let's do a little more than an opinion. Let's see if we can educate them. Maybe we can educate someone today, okay? Here, Klingon comes to Earth, and good old Uncle Sam stands next to him, and he says, I don't understand your language, Sam. What is that? He says, table. And so the question is a table made out of legs, a board, atoms, molecules? Absolutely not. Table is made out of a single piece. Okay, we got that? Table, the word table, single piece. It's that whole thing. Okay? It's not made out of parts and not made out, you don't say table and say, well, but it's got legs, it's got a board, I can sit on it, I can put a dish on it. Nah. Table is that which I pointed to. And that thing, at that moment, is made out of a single piece. That's how you present objects in physics. Okay, let's try something a little more difficult. Let's try the word chair. Chair is also made out of a single piece. So, hold it, Bill. It's got some boards there. It's got some legs. It's got a seat. Sorry, the word chair refers to that whole thing. So when I say chair, I'm referring to that whole thing. That's made out of a single piece. Not made out of atoms, not made out of molecules, not made out of anything. Okay? It's made of a single piece. Continuous, right? And here we have the word tree. I hope you're learning some language today, So what things are, okay? Tree, and you point to it. No, but it's got leaves and branches and roots. No, bark, no. No, it's made of a single piece. The word tree refers to that thing that's made out of a single piece. Okay, so where does the problem come in? Well, these people say, well, what about mediums? Media. And here you have one, and Sam points and says, ocean. Says, oh, but an ocean is made out of water and all these drops and H2O and... No. An ocean is not made out of fish, out of boots, out of dead people. None of that. No. Ocean is made of a single piece. Now, in this case, maybe I forgot to put the edges to the ocean. Okay, here, let's put some edges there. Okay. But ocean is made out of a single piece. That's what I'm pointing to there, or what Sam is pointing to there. That's an ocean. Okay. The whole thing is an ocean. Ocean refers to the whole shebang. Doesn't refer to a little piece of water. And this is what these people don't understand. They start saying, oh, the ether, it's a blob that covers the entire universe. I'm going to take a little piece of it and show you, how the ether does electricity or gravity or whatever. Now, you can't do that because you defined or you pointed to this blob that is the whole universe and it's made out of a single piece. So you cannot take a chunk of that and say, I'm going to do something with this little piece of ether. No way. No way. You're contradicting yourself already. And that's what these people want to do. They say, it's made out of parts so that I can take little pieces of it out. That's why we ask them to illustrate, okay? And then we have here the air, okay? Another big problem for a lot of people. People get so confused with air. It's a gas, and it's color-coded there with light blue, I guess, unless you're colorblind. Okay, is air made out of particles? Is air made out of molecules and atoms? Absolutely not. Air is that whole shebang that you see there, the whole bluish, light blue thing that you see there. That's air. Okay, and here's air around the Earth, and that's what air looks like. If you color code air, that's more or less what you would see. You would see, all this. In 2 dimensions would be a ring, and in 3 dimensions it would be, like a shell or covering of the Earth. In fact, let's remove the Earth from there so that you can see the air better without the Earth. There you see it. That's air. Looks like a shell, maybe a ring if it's 2D. That's air. Air looks like that. And one of the big problems that a lot of these people have is they say, they're under the impression that you need pressure, that when you introduce particles, they tend to move to the area of lower density. And so they say you need some kind of wall to contain all that stuff, because otherwise the particles will fly away to a region of lower density. Well, the Earth is not covered by any walls. God did not make a sheath around the Earth, around the air. The air can leave if it wants to. There's nothing blocking the exit of air from the Earth. And so the question is, where you see the black stuff out there on the outside, that's lower density. That's space. That's vacuum. Almost, perfect vacuum, but certainly much less dense than the air that's covering the Earth. So why doesn't the air leave and go to areas of lower density if there's no, container, no sheath covering the Earth? God didn't make one, the air is free to go, and it doesn't go. It stays there. And so, these people are wrong. These people don't understand basic physics, and they start saying, the air would go to a region of lower density. And here you can see it doesn't. It stays there. And so we have to show why it stays there. And it's got to do with gravity. Okay. And but let's continue here. And here we have the astronaut. And he's going to take a balloon full of air. He's going to pop it in the middle of nowhere. That's the second frame there. And he pops it. And what comes out is air. We color-coded it white so that you could see it. And that blob there, that's made out of a single piece. Air is the whole thing. Air is not made of molecules. It's not made of particles. It's not made of atoms. Air is the whole thing. The whole ball of gas, the blob of gas, that's air. When you say air, you point to the whole thing. You don't start breaking it up in pieces and say, well, this piece of air and that piece of air. No, air is the whole thing. And these people have a lot of trouble understanding these basic, kindergarten stuff. And here, why not? We point to a rope. So, a rope is made out of 2 strands. No. Rope is what I pointed to. The whole thing is made out of a single piece. Oh, but it's got different colors. Yeah, I'm sorry. I should have colored them with a single piece. Rope is what you see there, the whole thing. It's not made of parts. Okay? And so, in physics, every object that is presented is made of a single piece. If the colors distract you, just try to get a little Daltonism and, forget about the colors. Rope is 2 twined threads made of a single piece. That's what I pointed to. That's a rope. And so this guy's, they want to introduce notions which they never thought about, obviously. And they say, medium is made out of particles, and we take a chunk here and a chunk there, and we do whatever we want with it. No. Ocean, air, rope, made of a single piece, always. Okay, when you present it in physics. Okay, then you can move the whole thing any way you want. That's what you got to do with ether. Ether is made out of a single piece. Okay, so whatever ether is, just draw it and then do whatever you want with it. And of course they can, because they want the ether to be a concept, a blob that occupies all of space, meaning up to infinity, and it covers everything. And at the same time, it's made out of a single piece. It's continuous, it's not made of parts, and at the same time they want to take a chunk of it and say, look what the ether did over here. No, you can't do that. You're cheating. Okay? You already contradicted yourself. Okay, one fellow says the mechanism makes no sense and is inconsistent with the inverse square law. He's talking about my video where I showed that objects approach each other, and as they do, as the distance decreases, and there we have Newton's gravitational equation, or part of it. As they do, the ropes fan out. And so the closer they get, the faster they come to each other, acceleration of gravity. Why? Because the ropes fan out. There's more and more independent ropes, okay, simply as a function of distance. And these people they can't understand something as simple as that. And so he says it should be inconsistent with tension dropping off with the square of a distance. And what's the problem here? The problem is the word tension. These people don't understand what tension is. They have the irrational notion of mathematics, of the religion of mathematics, of what tension is. And let's just show one more time here. It says when this astronaut hits the ground, showed the astronaut coming towards the Earth, the ropes fanning out as he approaches the Earth, right? Isn't there even more ropes around him? I don't know what he's talking about. I mean, is he being hung by a rope? I mean, I don't know what you mean around him. Are they stuck to every one of his atoms? That's so. There are not more ropes. What we have is more independent ropes. They're not on the same axis. As the guy approaches the Earth, the ropes fan out. What part don't you understand about this simple baby kindergarten stuff? It just boggles the mind. The way you depict the ropes implies to me that there would be a stronger tension further away than close by. And again, he doesn't understand what tension is. We need to explain tension, not the mathematical tension he learned at the monastery. We're talking about physical tension, which is a totally different thing than what the mathematicians have out there, okay? And that's where he gets confused, because he's thinking of mathematical tension, not about physical tension, which is the opposite of what is required by Newton's gravity equation, which follows an inverse square law, and he just goes on there and on and on. Okay, so he's talking about tension. The tension is always the same on every rope in the universe. It's dictated by the velocity of light, c, 300,000 kilometers per second, which is a constant. Now, light always travels at the same speed. Why? Because it's the tension on the rope, which is the torsion that we have on a tense rope. And so the rope becomes flexible, except under certain circumstances, but normally they don't between atoms, right? And what happens is that you have torsion of that rope, and you have light traveling at c, because the tension on the rope is always the same. All you change is the frequency versus the wavelength, meaning the frequency, number of links versus how long the links are. Very simple stuff. Really very simple stuff. This is kindergarten stuff. The universe is a very simple place. The mathematicians have made it a complicated place because they started taking measurements, doing equations, say, oh, I don't understand all that stuff. Of course you don't. But Mother Nature never went to school. She just deals with rocks, planets, particles, atoms. She just moves one atom at a time from one place to another. So does Father Universe. They don't know anything about math. These relations that humans created. They know nothing, and they never went to school. Okay, so another fellow along the same lines says, I understand the ropes to be under some level of stress, and said stress might have to be attached to a star rather than just other earthbound atoms. Yeah, again, these people are talking about tension and stress. And so let's find out what tension and stress are in physics, because these people don't understand that. First, let me illustrate this, okay, here. Just so you know, the mechanism for gravity is right there. You can see it on the left. As the cylinder approaches the cube, the ropes fan out. So originally they were all these atoms were on the same axis. So it's like a single rope tugging, you could say number 1 to number 6. It's like 2, 3, and 4 do not exist because they're on the same axis. So number 1 is tugging from number 6. But what happens? As the cylinder approaches the cube, because of distance, because only the change in distance, we see more ropes. Each one that was on the same axis before, now they're all on different axes. And what happens is now you have greater tug because every rope is acting independently, what we call an effective rope. And there on the right, you see what happens at far distances, far away distances. What you have is all the ropes come together and act as a single coaxial, so gravity is very weak. And as it approaches, the cylinder approaches the cube, what you see is the ropes fan out, and you have all ropes acting independently. There you have the acceleration of gravity in a mechanism. Okay, something mathematical physics has never been able to do. Okay, and so what's the issue? Okay, so here, let's go with what this word tension means, stress, Here's from the Stack Exchange. The tension is the stretching of the rope at molecular level. No, that's not what tension is. What these people are saying is that tension is a pull, two pulls. In other words, a force. And the greater the tension, meaning the greater you stretch something, the atoms are all, or the molecules, right? They're all tugging and trying to stretch with respect to each other. That's not tension. That's called pull. Pull is a force. Tension is not a force. Not in physics. Tension is when we reach a stalemate, when no one wins the tug of war. Okay? When everything is stretched to the limit. Like the rope, because see, the thread that makes up the rope is made of a single piece. It doesn't stretch. We don't create matter by stretching the thread. That doesn't happen under a rope model. There's only so much matter in the universe. It's a finite amount of matter because there's a single thread that makes up all the atoms, which are connected to each other by ropes, all of it made by the same thread. Okay? And so here we have again the Wikipedia version of tension. It says, tension is described as the pulling force. Yeah, they're talking about pull. They're talking about a force. They're not talking about tension. But they put numbers to these things, and they say, oh, the tension is so much because one's pulling from here and the other one's pulling from over there. So they say, what's the tension? How much tension is there? And they talk about quantities of tension. That's where the problem is. No, tension, that's pull. That's called pull. One's pulling here, one's pulling there. Even if the elephant stands still and you're pulling on it, the elephant is pulling on you because he's this great inertia, this block that's preventing you from taking the elephant with you. Okay, so the elephant is pulling on you no matter what. It's called pull. It's not called tension. Tension is something else. And here's another definition just in case. Tension is a force, and they go through all this stuff showing that you need an elongated object to produce tension because it's a pull force. It's not tension what they've been talking about for the last 400 years. They're talking about pull, a force. And here's an example, okay? It says, there are two people, A and B, in space with taut rope, no tension currently in between them. If only A is pulling and B is not, then the tension is equal to the force A exerts. If B is also pulling, both of them pull from either side with a force of 100 newtons. Then the rope at the end of B will pull B with a force of 100 newton, and by Newton's third law, the rope will experience a pull of 100 newton. But B is also pulling his end of the rope with 100 newtons. So I guess we have 200 newtons of force, not of tension, of force. So whenever you pull, if you still haven't finished stretching, whatever you're stretching, then we have pull. We don't have tension. So far we have no tension. Tension is a tug of war where no one wins the game. There's a tie game, or better yet, I like to say it in different ways, and you better sit down and listen to this. Tension is a stick made of a single piece between two objects. Let me repeat that. Tension, yes, stress is when you put a stick made out of a single piece between two objects, a dumbbell, in other words. And I think these guys are the dumbbells. A dumbbell is tension. That's what it is in physics. Tension means nobody wins the tug of war. If someone is winning the tug of war, you have pull, not tension. Okay, so along the same lines, one fellow says, what happens to atoms at the edge of the universe when atoms are destroyed in a nuclear explosion? He's talking about the thread or rope version of the atom, right? Do threads break in such circumstances? And so here are the answers very quickly. Really, atoms are indestructible, okay? It's made out of a single piece of thread throughout the universe, so every atom is made of that same thread. and it's a single closed loop thread, so that's all there is in the universe. If we untangled every atom, every rope in the universe, we would end up with a single thread. Enormously big, very thin, and made of a single piece, malleable, etc. Those are the characteristics. Naked atoms release neutrons and decay swiftly to smaller non-radioactive atoms. Yeah, but, in other words, when you have nuked atoms, I'm sorry, when you have a nuke, an explosion, all you have is decay of the atoms. So if you have uranium, it'll decay, I don't know, to radon or to even lower to lead, which is non-radioactive. So that's all you have. So there is no disintegration of the ultimate atom, which is the hydrogen atom. That's the only real atom that exists out there. All the others are composites of the hydrogen atom. More hydrogen atoms together with neutrons, they make up bigger atoms. That's all we have today. But if you break it all apart, you end up finally with neutrons on the one hand and hydrogen atoms on the other. That's all there is, ultimately. Single thread is made of a single piece, okay? And again, it underlies all atoms that interconnect them, right? The single thread. And single thread is not made of parts. It's not made of discrete segments or little dots or anything. Points. It's made of a single piece. Okay, it doesn't stretch because it's made out of a single piece. Okay, single thread cannot break or be cut. Okay, you cannot break it. And so yeah, the single thread is what makes up everything in the universe. That's our hypothesis, called an assumption. We make an assumption so that you can understand the theories founded upon that assumption. Okay, here we have a fellow. He says, the fundamental single thread, trillions of times smaller than the Planck length. Yeah, could be even more than trillions, maybe quadrillions. I mean, there's you have the Planck length, and I just drew more or less, right? Obviously, Planck length is very small, but the thread is maybe thinner than the Planck length. It's no problem in physics. That's just a question of smallness. So we have no problem with how big, how fat things are. That's a concern for mathematicians. Okay, the fellow says, gravity counteracts the depressurization. And what is he talking about? He's saying, again, what I said earlier, that you have air around the Earth. Why doesn't it leave? Why does it go to a region of lower density, which is space? Is there a sheath or a container, holding the air in around the Earth? And the answer is no. What's holding it in is gravity. But he says gravity is what holds the air in. But that's like saying love counteracts intelligence. You haven't told me what physical entity is holding each atom of air. So forget about using words like gravity and light in very generic terms. Talk about one atom of air that makes up the air and one atom on Earth. Why does this atom not leave? Why doesn't it fall? Okay, you might say, well, it doesn't fall because there's too much density. Fine, forget about that one. Why doesn't it leave? That's the question. What holds that atom there? And hopefully there's a physical mediator between that atom out there and the atom in the Earth. Because if you're saying that there's no mediator because you cannot see or touch something between them, you're going to be doing what is known as action at a distance, which is the scientific term for black magic and witchcraft. You're saying it just happens by remote control. So just be aware of that. Okay, let's continue here. We have, this fellow says, if a black hole is nothing more than a densely packed collection of matter that is hard to see, absolutely not. I have to stop you right there, and I can't deal with the rest of it because you already failed. You failed kindergarten physics. You're not paying attention to what's going on in the world. So let's put some authority. How about Stephen Hawking? I mean, is he an authority or what on this kind of stuff, right? He should know. Here it is. This is what he tells you. Listen carefully, because people are not listening to what people like Stephen Hawking is telling them in their face. They're not listening to Stephen Hawking. So please listen to Stephen Hawking. Don't listen to me. I don't know what I'm talking about, but he probably knows what he's talking about, right? Okay, here it is. So he says the following. He says, Eddington was shocked by the implication, that a black hole, in other words, a star, right, before it becomes a black hole, would collapse to infinite density. Infinite density. I hope you understand what the word infinite or term infinite density means. Okay? And he continues, refused to believe Chandrasekhar's results. Eddington thought it was simply not possible that a star would collapse to a point. What is a point? Zero dimensional. That's what a point is. Euclid told us that, that which has no part, right? Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. Let me repeat that because you probably didn't hear it. Zero size. We're talking about no volume, no shape, no radius, no diameter, no nothing. There's nothing there. Zero size. Do you understand what zero size means? So this thing that this fellow says that it's small, this is the notion people have. It's nothing more than a densely packed collection of matter that is hard to see. They're thinking that a black hole singularity, is tiny. And what's the issue? The issue is the mathematicians introduced lousy language that helps them but doesn't help understanding at all. And the word is infinitesimal. And when they say infinitesimal, they have this duality. They mean two things at the same time. Infinitesimally means very, very small, getting smaller, and it also means zero. It means both. That's what the mathematician means by infinitesimally small, like saying, I didn't go any further, I didn't see how small it got, I just say it just kept getting smaller, smaller, and smaller, and smaller. But it's still small. It's still something there. The onion, you peel the onion, you still find onion in there, no matter what. It's not like it gets smaller and disappears, right? It gets smaller, smaller, and smaller until it gets infinitesimally small, by which later on they treat it as zero, as nothing. And that's where we have a problem, because either the singularity of a black hole is zero size, zero shape, zero volume, or it has some volume, whatever that may be. I don't care. If it has volume, it's a thing. But if it doesn't have volume, it's not a thing. It's called space, empty space, vacuum, nothing. Okay, so let's get the language right. And the question here is that people have missed the language. They allow these people to get away with murder. Okay, they say, oh, infinitesimally small. I understand that. No, you don't, because they're saying zero at the same time they're saying small. And here, just in case, we have another fellow from Cambridge, and he says the following: on solving the equation with particular value rho of central density, you will get a model of a star with mass m, radius r. Plot r as a function of m and show that r, the radius, right, radius, falls to zero. Radius falls to zero. What can that possibly mean? Radius falls to zero when m is equal to the Chandrasekhar mass. If you can do all these, then you have repeated the calculation for which Chandrasekhar won the Nobel Prize. He won the Nobel Prize, Subramanian Chandrasekhar, for proving mathematically that a star collapses to nothing, to zero size, to a singularity. No volume, no diameter, no radius, no shape, no nothing. It's a definition of nothing. In fact, it has no mass either, because it crushes all matter out of existence, and mass is the quantity of matter, or a measure of quantity of matter. There's no matter inside the singularity of a black hole, so it has no mass either. But even if we concede all that, how does non-existent singularity, I'll give them even the density, I'll give them gazillions of tons, no problem. I'll just concede kilograms. How do kilograms move a star? Like they say, the star is rolling around a black hole. There's nothing there. We can't see it, but the star is rolling, so there's got to be a black hole, a lot of mass there. Fine, we'll concede the mass, we'll concede the kilogram. How does the kilogram move the star? I need to see the mechanism, okay? And hopefully it's not, what is it? Kilograms on, number lines, known as space-time. And we're going to deal with that next. Okay, a couple more issues here. One is touch, a touchy issue. And everybody likes to ask this, you know, they're concerned about touch. If the rope thread here, what is it that prevents some things from melding together and cause other things to become one with each other? Okay, and I don't like to talk about this touchy issue. It's in the book, okay, I was saying, so it's there, it's registered anyways, it's not like I'm going to give you a different version of what's in the book. But it's several pages, okay, and I don't cover this subject first because these people, a lot of these people, they don't understand kindergarten stuff. You know, I'm not going to get into the very touchy issue of touch, okay, it's very complex. And these people can't understand simple stuff, let alone something as complicated as that. I'm just going to give you a couple of scenarios, 3 of them here. One has to do with aggregation. A lot of threads, remember, around the atom. Okay, that forms the shell of the atom, our atom, the atom that we have under the rope model. Okay, and so you have several windings, many windings. I don't know how many. All I'm saying is there's several windings of thread around the every atom. Hydrogen atom. And again, there's only hydrogen atoms. All the rest are just composites of hydrogen atoms. Then you have backscattering. Rutherford, 1919, ended up doing some experiments, and he found out that when he shot some particles against an atom, most of them went through, but some of them bounced back. He said it was like shooting cannonballs at paper tissue and finding the cannonball bounce backwards. And he could not understand that, but he concluded from that the atom was mostly empty space. Well, what was mostly empty space was, you know, the space between his ears. That's what it was, because he reached the conclusion that's irrational. No, an atom is not mostly empty space. It's that their touch is absent from the atom. The only way you can get neutron bombardment to go through is first speed. You have to have speed. The other one is, again, if the neutron goes through one of the sides, it doesn't go exactly in the center, and it hits center-wise the atom, then it can go through. But if it hits right in the center, it bounces back. Okay, that's more or less our explanation. That's the quick one. Okay, you got to go to the book to see it in more detail. Okay, but that's in general terms. And then the other one is magnetism. Do the threads touch each other? Yes, they do. I hate to say that here because people say, oh, they touch. No, they don't touch. But for the purposes of magnetism, we have these walls of thread. Walls, aggregation. Okay, you have many walls. Think of paddle wheels of a riverboat, but gazillions of paddles, okay, all around. And they're going like that. And so they repel. And if one goes up and the other one comes down, then they attract. Why? Because there's this very light friction that becomes a monster when you have aggregation. Okay? And that's just in a nutshell, more or less the ideas. There's a lot more. You got to go and look at it in the book. I try to stay away from that subject because, again, people do not understand because they don't know what neutron bombardment is or any a lot of those terms that, you know, the experiments that have been run throughout history. They have to get that first underneath their armpits before they can, you know, start asking questions. Okay, and final issue, a fellow says, would you call yourself a materialist? And he goes on with that, saying that I seem to be the only materialist out there, and in a sense I agree with him. A lot of people who call themselves materialists end up being spiritualists. You know, they start using concepts as physical objects because they never went through kindergarten physics. But there you have it, something that which has shape, and so, you know, you can't do physics without an object, and that is the golden principle of physics. You can't do physics without an object, because if you do physics without an object, like they used to do in the past, like spirits, you know, and so on, well, you're doing black magic. You're doing action at a distance. You're saying there's no mediator out there, but things happen from a distance. And that is very scary. It's called, again, black magic or witchcraft.